So the way I think we're gonna start these more product-based sessions is we're gonna just start off with a current event. And so one current event that we have going on right now, I don't know if this will switch to the next, there we go. The largest ever VRF project is underway in Egypt. So Egypt's building a new capital administrative city, and they are installing 280,000 tons of VRF in their residential section of the new administrative district. And some things that we're going to talk about today are some of the reasons why Egypt chose to utilize VRF for their 22,000 apartments. And the reasons why they chose to use VRF was one, the high efficiency. So every single one of those apartments is going to be fed by condensing units with inverter compressors. Those compressors can drive the flow of the refrigerant exactly to the load, right? So you've got very efficient systems for all of those apartments. VRF is modular, right? So as they build new apartments, they can build the VRF as those apartments go in, right? So when you have a central plant, you have to build for your total capacity, and then you're going to have some down and idle time. VRF's modular, so as you build more apartments, you build more systems and install more systems. The deserts of Egypt, there's no water, and so or there's not a lot of water. So having an air-cooled system means you don't need water, and so working with the utilities you have is important for planning these projects. And then again, no central plant, right? So they don't need a huge facility crew to maintain a central district plant that's going to be running, that has to operate all the pumps and everything that a hydronics-based system would utilize. So just kind of a cool current event that's going on right now. This should be done by 2028, but yeah, the largest VRF project ever in the world. So kind of a cool way to start the presentation. And we're gonna hit on some of these items in the presentation. So I will throw it over to Jack, who can take it away from here.
All right, everybody. Thanks, Matt, for that introduction. Just a little current events before we dive into the technical stuff. As we'll go through the presentation, you'll see, not only is VRF great for something of this scale, but you can even use it down to, a 1 or 2 room system. So we'll dive right into it. Another quick overview of who I am. My name is Jack. I am the VP of Engineering at Cadent Energy Solutions. We are equipment manufacturer reps. So you can reach out to us to help with selecting equipment, sizing, equipment, picking which types of HVAC components and devices you want to put into your building. We can get you cut sheets and work with that. I went to Notre Dame, got my bachelor's in mechanical engineering. I am a licensed PE, professional engineer, and I started my career at CMTA back when it was AMA Group. Shout out to those who might be on the call. And then I guess an introduction for Matt, since I don't have a slide for him, but he's actually the owner of Cadent Energy Solutions. Has been doing this for a long time now, and he's the guru in our office on putting hands onto all the equipment and knowing the ins and outs of all of it. So a little zoom out. Today, we're talking about VRF fundamentals. Next week, we're going to talk about RTUs, rooftops, and package systems. So if you go onto our website, you'll see that this is updated. I think we just updated it earlier today. If you saw, we had air-cooled chillers on there for next week, but we're actually going to move that a little bit later on in the summer until we cover some of the more basic equipment, and then we'll dive into the complicated stuff later on. As with last week's presentation, I'm going to give you a promise, and by the end of the presentation, you'll be able to do all 4 of these things, just to be clear about where we're going and what we're doing. So first thing, what are VRF systems and which system loops does it use? Last week, we talked all about the train fundamentals course and how they explain every type of HVAC system can be tracked back to one of the 5 system loops or multiples of them. So the second promise is we're going to dive into the components. We're going to look at how each one of the pieces of a VRF system operates and what function it plays in the overall heat transfer role. Third, take away from the equipment, right? We're going to learn about what advantages and disadvantages VRF has, right? It's not perfect for every solution, but as Matt kind of said, we can scale up to these massive complexes and buildings, or we can go down to a small 2-3 room system. And we'll talk about that later on. And then the last thing is we're going to go through some examples. As always, we're going to run through real world examples of whether or not we should use this tool that's in our tool chest for that specific project. All right, so last week, and our overarching theme of our entire series is how do we move heat, right? These are the 5 system loops that Train kind of outlines for us. They're listed at the bottom of the screen here. If you look just in general at the left picture, we're trying to move heat from our occupied space all the way through our 4 loops at the bottom to the ambient air, right? Somehow we have to get the heat from our occupied space outside, right? And we're going to use one of these 5 loops, combination of a couple loops in order to do so. So how does VRF look? We're just using controls, our supply air loop, and our refrigeration loops. We don't have any chilled water, as Matt said earlier, right? Desert application, you don't have anything, but it can be applied for a wide variety of applications that also don't want to use chilled water or don't want to use condenser water. So in this VRF application, we're taking advantage of using 3 system loops. So what does this look like? We're going to take a high level view of this first. So essentially, if you look here, we'll have 3 or 4 main components to our VRF systems. It's going to be our indoor units, right? These are the devices that sit in our occupied space. We're going to have outdoor units that sit outside. These actually reject the heat into the ambient air. And we have refrigerant piping that connects all of it, right? Somehow that heat needs to move from the indoor units to the outdoor units. That medium is the refrigerant piping. In this situation, this is a heat pump VRF system where all of our units are heating or all of our units are cooling. The outdoor unit is just going to switch between heating and cooling modes. And this diagram shows the heat recovery, right? And this is actually the most powerful layout that we can use in VRF systems. It allows you to have individual zone control. If you want to feed a whole office space, you're going to have, dozens of offices. All of them are going to have various loads. Maybe one of them is in the shady side of the building and the other one's in the hot, sunny side of the building. You're going to want to be able to cool those sunny zones, and you're going to want to be able to heat potentially those shady zones. So in a heat recovery system, you still have your indoor units, you still have your outdoor unit and your refrigerant piping. The only difference is we have this BC controller, as it says on this diagram, or valve port box or branch selector. There's a bunch of different names for it, but they all actually act as the same purpose. It just distributes the refrigerant in a little bit different way than if you were in a heat pump system. So again, at a high level, we have outdoor units, indoor units, refrigerant piping, and our controls that tie them all together, right? So what is our variable refrigerant flow system? It's all of these components combined, working together in order to move our heat from inside to outside. And another way of kind of showing that, right? We have just our 3 system loops, our control loop, our air side loop, and refrigerant loop. Connected with our indoor and outdoor units. As you can see, both of those components are part of our refrigeration cycle, and then our evaporator is our bridge between the 2. And just in general, we're moving our heat from left to right, occupied space out to our ambient air. So now section one, we're done. We looked at what we can kind of identify at a high level what VRF systems look like, the components that are in them, and whether they're set up as a heat pump or a heat recovery system. Just at a high level, we're going to dive into it a little bit more in this next section, right? So we're going to talk about the components, the actual physics that they all use, and how they actually act and function in the system to move that heat. Our refrigeration cycle is the bread and butter of our whole industry, right? Without the refrigeration cycle, we are not going to be able to move heat against the gradient. Last week, we talked about the laws of thermodynamics. The second law of thermodynamics says heat naturally moves from hot to cold, right? Or high energy states to low energy states. Essentially, that works great if it was always colder outside than it was inside. But we know we live in the real world, and we have to have situations where we're rejecting our heat from a hot indoor space to an even hotter outdoor space. We need to put in work, right? And so our four components here are compressor, condenser, expansion valve, and evaporator. Each one of these components is key in our VRF system because our VRF system is basically expanded and distributed throughout the entire building. Right? We have that refrigerant piping connects from outside to inside, and that runs throughout the building. It's essentially a refrigeration cycle throughout the whole thing. And again, another way of kind of looking at it, right? Moving that heat from occupied space to the ambient air. As I said, we got to go from hot to cold and then hot to cold. So if we're moving from indoor at 75 degrees, the only way that's going to work is if the coil, the refrigerant coil, is colder. So 75 degrees transfers into 45. We have to add in our work according to the law of second law of thermodynamics in order to get our refrigerant hot enough to reject into a 95-degree ambient temperature, right? So all we're doing is playing a little trick by adding in work in order to make sure our refrigerant temperatures can reject heat and absorb heat in our indoor space and our outdoor space, right? It's all about getting the right temperature because we know heat only moves naturally from hot to cold. But what exactly does adding in the work mean, right? We can just wave our hands and say, I don't want to think about it anymore, but we're going to dive into it a little bit. So looking at our compressor, that's where our work is actually put in. All we're doing is manipulating the pressure of our refrigerant in order to make it hotter, right? And so the properties of refrigerants in any fluid, you're going to be able to manipulate the pressure in order to affect the temperature, right? So our compressor is adding in work and adding in pressure in order to increase our temperature, right? That's how we get from the 45-degree evaporator temp to 115-degree condenser temp. All we're doing is adding in pressure, right? And it's the same thing on the reverse side of the loop in our stage number 3, the expansion valve. All we're doing is reducing the pressure in order to lower the temperature, right? To get from that 115 degrees down to 45. We're just taking advantage of the properties of refrigerant in order to make this, hot and cold side work for us in a continuous loop. One other important thing to note about the cycle is that we are not changing the temperature when we're changing phase, right? So if we go back to the previous slide, right, we can see that in our evaporator and our condenser, we're changing phase. And in our expansion valve and compressor, we're actually changing pressure. So if we go back to this slide, we're changing the pressure at the top and the bottom, and we're changing the state and the phase of the refrigerant on the left and the right. So in another way to kind of put it, we can see that the left side in this situation is going to be our low pressure, low temperature side, and our condenser is going to be our high pressure, high temperature side, right? We're manipulating the pressure to achieve the temperatures that we need. And as I just said, right, we're moving heat by phase change, right? So our evaporator and our condenser, we're not changing temperature, we're changing the phase. Very important property of refrigerant and any fluid is that by changing the state, we actually pack a bigger punch in BTU transfer, right? So we're actually moving a lot more BTUs by changing the phase than we are just by changing the temperature. So really the most powerful way we can move heat is by evaporating or condensing our refrigerant, not by just changing the temperature of it. So zooming back out a little bit after that, a little bit of a physics dive, we're looking at these are our puzzle pieces, right? So when we talk about VRF systems, we talk about our outdoor units, indoor units, controls, and our branch boxes. This is what they look like, right? Our indoor units are going to have a fan and a coil, right? And we're going to deliver that air into our space because that's where our refrigeration cycle and our air side cycle meet. We have to have some way of moving the heat on the air side and some way of moving the heat on the refrigerant side. Our outdoor unit, these things sit outside. They reject the heat into the ambient air and they're air cooled. And our controls and branch boxes are just the intermediate devices that allow for that system to operate efficiently. So looking at our outdoor units, right, where does this fit in our refrigeration cycle? It's components 1 and 2, right? It's our compressor and our condenser, right? This portion of the refrigeration cycle, as we recall, is adding in the pressure, right? Our compressor does the work in order to increase the pressure and increase the temperature so that we can reject to the ambient air. These are called air-cooled condensing units sometimes, so you'll see them on drawings with the tag of ACCU. That's just because air-cooled is the medium that we're transferring the heat to the outside, and a condensing unit is just the type of equipment it is. So at a high level, right, we're looking at our components 1 and 2 in our refrigeration cycle with our outdoor units. At our indoor units, these are called fan coil units or air handling units, right? Our FCUs and our AHUs. As I said, these are ducted. Some of them can be ducted and some of them are not ducted, but essentially they all have fans to move the air and they all have a coil with the refrigerant in them. So talking about the refrigeration cycle, these are components 3 and 4, right? This has our expansion valve where we are decreasing our pressure, and it has the evaporator where we are evaporating our liquid into vapor and transferring the heat. These all sit in our occupied space as well. And what do our branch controllers and valve port boxes do, right? We're talking about our heat recovery systems. These are the devices that distribute the refrigerant to the zones that need them. So it's essentially a box with a handful of valves that will open and close depending on which zones and which indoor units need the heating, the cooling, or how little heating or how little cooling it needs, right? And so it has the valves. It has a certain number of ports, right? So every indoor unit needs to have its own dedicated pair of ports. So they come in, there's various sizes by various manufacturers, but they generally come in, 1, 4, 8, and 12 ports. Some manufacturers have more, some just have 1 or 4. Essentially, this tells you the number of ports dictates the number of indoor units, right? So if you have 4 ports, you have 4 indoor units that it can distribute the refrigerant to. And this device also allows you to get your simultaneous heating and cooling, right? The powerful part of VRF with the heat recovery is that you'll have zones in the shady side of the building and the sunny side of the building that'll need heating and cooling at the same time, right? This box is what allows the hot vapor to go to the heating zones, and it allows the low pressure liquid to go to the zones that need cooling. It's basically just your distribution box that allows refrigerant to go one place or the other. So what makes VRF variable refrigerant flow, right? And what differentiates it from any other piece of equipment that uses the refrigeration cycle in the air side loop? The powerful components are our expansion valve and our variable compressors, right? So EEV is electronic expansion valve. You can see it on the left side. in the picture, this device is where we're reducing our pressure, right, in order to get the right cold temperature at our indoor units. Every indoor unit has an EEV, right? And so when the thermostat in the room is calling for lots of cooling or lots of heating, that valve is wide open. It's trying to get as much refrigerant into the coil as possible so that you can evaporate your refrigerant and get lots of heat transfer. Conversely, when your zone's satisfied and your temperature in your room is exactly where you need it to be, that electronic expansion valve or your EEV starts to close. Less refrigerant goes through the coil. You have less evaporation or condensing, and you have less heat transfer, right? So all it is modulating the flow at every indoor unit so that every indoor unit can operate off its own temperature demand, right? So you're not affecting your whole system when one zone is satisfied. You're actually catering to each individual zone's demand. And so the other side of the story, right, the other side of our refrigeration cycle is our compressor, right? In VRF systems, it is a variable speed compressor, right? So you can imagine if you are closing your valves in some zones, you can't just keep cranking that. I guess a better way to think about it is your EEV is your zone level control and your compressor is your total system capacity, right? So if all your zones are all calling for full heating or full cooling, that compressor is at its full speed, right? Because you need as much refrigerant flowing as you can to get to every single zone. However, as each zone starts to get satisfied, those valves on the electronic expansion valve start to close. Once 1, 2, 3, 4 zones start to cater down and taper down the amount of refrigerant they need, you got to slow down your compressor too, right? So your 20-ton system can actually ramp down if your compressor speed slows down to get to a 10-ton, a 12-ton, or a 14 tons of actual demand load, right? And so these two components and sides of the refrigeration cycle work together in order to meet your exact demand. And that's the powerful part of VRFs, right? So more refrigerant flow means more capacity. Less refrigerant flow means less capacity. And your EEV and your variable speed compressor work together to make sure that every zone gets the correct amount of flow, depending on how much cooling you're heating. So another caveat of VRF systems and just the way that it varies the pressure, right? And so if your valves are opening and closing, you're varying the pressure. If your we're varying the pressure in our systems. And as we said before, that actually changes the temperature of our coils. So if your full system is mostly meeting its demand, right? Most of the zone's temperatures are satisfied. Then our compressor starts to slow down because all of our EEVs are starting to close. The consequence of this is that we're not changing our pressure as much and we're not getting as much temperature change. So when we're running at full load on the left side, our coil temperature is quite cold, right? And so we're going to get a lot of condensation buildup on our coils. We're going to take the humidity out of the air, and that's really good for latent loads, right? So whenever your coil temperature is low, you're going to condense water out of the air and remove the moisture. However, on the right side, when you're at part load and our compressor speed is low, we're not going to get as low of a temperature at our coil. And the consequence means we're going to slowly drift above our dew point and we're not going to get any moisture removal at our coil. This can be problematic when you have high outside air loads or there's a lot of moisture in your space that you need to remove. If our coil isn't cold enough, then we're not going to be able to remove that moisture. So that is a drawback of our VRF systems that definitely needs to be put into consideration when you're designing these systems. It's great at full loads, but our coil temp is going to drift above the dew point when we're at part loads. Just another thing to think about with these systems. Diving into our 2-pipe and our 3-pipe configurations, right? Our heat pump only needs 2 pipes. Essentially, every zone is operating in heating. And if you switch the compressor to cooling mode, or switch our system over to cooling mode, every single zone is going to be operating at cooling, right? So there's no way to get individual zone control in that system. The only way to get individual zone control, right, is with our heat recovery system, and that needs 3 pipes. The reason for the 3rd pipe is it is an intermediate vapor, right, that's going to run to our coils in order to get, it basically transfers heat between our zones instead of transferring that heat all the way back to the outdoor unit to then send it to the indoor unit, right? So you can imagine in the zones that are in cooling, right, you're pulling heat into our refrigerant, right? But if there's another zone across the building that needs heat, you can pull the heat out of our cooling zones and send it to our heating zones without running it through the compressor. That's a very, very powerful energy savings. And it's actually the best part about our VRF systems. Our heat recovery is going to allow the heat to be moved from hot zones to cold zones without using energy, putting in the work at our compressor. It's free cooling and free heating, and makes these VRF systems extremely energy efficient when you're using heat recovery. The caveat: you need that 3rd pipe. It's the only way to get that heat transfer across zones. I will say there is one manufacturer, Mitsubishi, who has heat recovery with 2 pipes. It has other consequences at our branch boxes. It's just another way of doing it. But for the most part, all manufacturers except for Mitsubishi use 3-pipe heat recovery. They all function the same way, right? But just one has 3 pipes and one has 2 pipes. We'll talk about the 3-pipe configuration here just to keep it easier without the exception. So the 3rd loop, right? Our controls loop, we haven't really talked about it yet, but that is actually what makes VRF so powerful, right? If we can modulate our EEVs and we can modulate the compressor speeds, dial it in exactly to what the demand is, we're going to have a really smart system that is very energy efficient, right? And so every single zone is going to have its own temperature control with the EEVs, and those EEVs are going to talk to our compressor to basically have more efficiency, right? We're not running all out unless we need to run all out. We're running at part loads, we're running at part speeds, and we're not using as much electricity in this situation. And it also allows us to use that free cooling, right? We're going to get free cooling between zones. Our branch boxes are going to smartly send the hot refrigerant to the zones that need it, and it's going to smartly send our liquid and low pressure vapor to the zones that need it for cooling, right? And all that is not possible unless we have a very, very smart control system, which is why the control loop is extremely important in our VRF. So now that we've dove into our components, right, we'll move on to asking ourselves the right questions, right? What are the advantages and disadvantages of VRF? We kind of touched upon all of them, but we're going to list them out here so that you can have a clear list of the advantages and disadvantages, or at least the major ones, so that when you have a project, you can right away determine if it's going to be possible for VRF to be used or not. So if you remember back to the last presentation, we talked about project constraints. This is a list of 10 questions or considerations that you should be looking at for a project when you're determining which piece of equipment to use, right? What system is best? How many system loops do I need, right? Which ones are going to work and which ones are not, right? We have a wide tool chest, right? There's many, many, many different types of equipment to use. Where do you start? By asking these questions so you can narrow down which ones work best. So before kind of telling you which ones work for VRF, we'll kind of go through them each again. So distance to heat rejection point, right? Is this going to be a major consideration for VRF? A little bit, right? We know we're sending our refrigerant throughout the building. instead of ductwork, right? This first and second questions and points that we're asking ourselves are kind of combined, right? And so in VRF systems, you're sending small refrigerant to a lot of zones. You're not sending ductwork. You don't have huge mechanical rooms. You don't have big plants. For the most part, your indoor units and your outdoor units are small. Your refrigerant piping is small. So if your architect is telling you you don't have a lot of space, maybe think about VRF as a solution. I think actually this is a better slide to show things. So right, so number 2 on our advantages of VRF on the left side, footprint equipment we just talked about, right? We have no chiller plants, no boiler rooms, no duct shafts, right? We're gonna have small refrigerant piping and small indoor and outdoor units. This can be a powerful tool when your architect tells you there's not a lot of space. Another major advantage of VRF, as we said, it can heat, cool, and do both at the same time, right? So if you have many, many different types of zones and the diversity between them, as I said, you're going to have sunny zones, you're going to have shady zones, you might have a huge conference room, or you might have, a little phone booth or storage closet. Those are going to have very different load profiles. VRF is flexible enough where you can send only the amount of refrigerant you need to that small zone, only the amount of refrigerant you need to the big zone, and that'll accomplish the amount of heating and cooling that you need. So it's a pretty powerful tool there if you have multiple zones and all of them require different amounts of heating or cooling. Another advantage of VRF, in New York State, we're getting rid of gas, right? We don't have the luxury of just throwing in a boiler or using direct fired or indirect fired gas heating to heat up our spaces. We got to go electric. So VRF is a powerful way to get your heating, right? So we use heat pump heating in these VRF systems, and you don't need natural gas. So it's a very powerful tool in the age of electrification. And lastly, energy efficiency. As we said, these systems are extrememely smart, right? We're going to have the controls be able to dial in every single zone. We're not wasting energy or we're not wasting heat by running our compressors and running more refrigerant than we need to each zone. This system is going to be able to smartly use the amount of electricity that it needs and no more, right? And so conversely, looking at some of the disadvantages of VRF, first cost, right? So if we're just simply, this is going to come down to what you're comparing it to ultimately, but VRF has a lot of controls. It has multiple components, right? And those are going to add up in cost. While they're small components, right, you're going to have more of them. So maybe versus a rooftop unit where it's only one packaged piece of equipment, you're actually going to be a little bit more expensive, but you're not going to get the same performance or the diversity or the zones, right? So it's a trade-off. In terms of first cost, right, it is a little bit pricier than a packaged rooftop unit, but if you're comparing it to a chiller plant, we're actually nowhere near as expensive. So it is a disadvantage when you're trying to keep things simple, but if you're trying to compare it to a huge chiller plant, you're actually going to win, right? So that's a disadvantage, but it depends. And the second disadvantage, right, we're running A2L refrigerants through these VRF systems, right? A2L is slightly flammable. It's a type of refrigerant class. And, we used to be able to run A1 refrigerants, which were not flammable at all. Now we're stuck using A2Ls. And there's all sorts of mitigation strategies that we didn't have to contend with before that are now required. So, at a high level, you want less refrigerant in order to stay under the concentration limits. So if you have small rooms or you have large heat loads and long pipe lengths, maybe this isn't the best system because you're going to have to implement mitigation strategies. It's pretty easy to overcome these strategies, right? There are a lot of smart ways to get away with A2L refrigerants. But maybe if you don't want to have to worry about that at all, you just say, I don't want to deal with A2L refrigerants in my space. So maybe VRF gets nixed right off the bat. But as I said, there are many ways to cope with the strategies that are not as hard as maybe people think. We just got to get familiar with them. Another disadvantage of VRF is building size and heat load, right? This one's more about heat load. I talked a little bit about the dew point and the temperature of the coils. Essentially, these VRF systems are not good at high humidity loads, right? High latent loads are not going to be able to be cooled down by our VRF system. At full loads, right? At full loads of our VRF system, we're going to be able to cool that and get rid of the humidity just fine because our coil temp is cold. But if we're running at part load, our coil temperatures creep up and we're not going to be able to remove the moisture. So if you have on your project high latent loads, you have to think about how to counterbalance that with a supplementary system. Right? We're going to usually use a DOAS system or an ERV system to whisk the moisture out of our outside air before it reaches our VRF. And lastly, this one doesn't have a number because it wasn't on our list of 10. As I said, there are way more than just 10 constraints you got to think about. But in this situation, for VRF, we got to think about our ambient operating conditions, right? So because we are using heat pumps and we're using pressures and we're manipulating our pressure to get the right temperature so that we can absorb and reject heat. Sometimes, and then you can imagine that's very dependent on the ambient temperature, right? So if we're at 95 degrees outside, we can perfectly handle that situation, right? We can get cooling at 95 degrees. We know we're getting our refrigerant all the way up to 115. Maybe we can push it, get to 120, right? But you're still going to be able to reject that heat to a 95 ambient. As it gets really, really hot, right, and gets to 120 degrees outside, which in the United States isn't as common, right? In New York State, that's basically non-existent. That's where you start to lose your efficiency and maybe you shouldn't use VRF. It actually works the same in reverse, right? So when we're heating, we have to think about what our ambient temperature is outside. So can we get our refrigerant temperature to be 0 degrees or less than 0 degrees on a low day, right? We want to be able to heat even though it's really, really, really cold outside. Otherwise, we don't have any heat in the winter, and that's a huge problem. So nowadays, almost every VRF system is going to be able to provide 100% heating down to 5-10 degrees Fahrenheit. And it's slowly going to derate down to -22. And, once we reach -22, manipulating our pressures is no longer going to work. We have to figure out a different way to heat. So if you know you're going to encounter days that are well below 5 degrees or well above 100 degrees, maybe you got to think about how we can get a different form of heating or cooling. All right, so we kind of just went over some major advantages and disadvantages. Right, our controls are really the most powerful part of our VRF system. That makes or breaks it. It's going to make it more powerful and more flexible, right, than other systems that we could use. So we're going to go in next, and we're just going to talk about a bunch of examples. I think this is the best way to look at all of these applications is to decide whether or not VRF is going to work there. So we're evaluating, our 10 constraints, maybe some other ones on the right side, but in scenario A here, right, we have a hotel or a multi-family building in New York City. It's a tight urban floor plate. There's many, many zones, as you can imagine, in a hotel or multifamily. There's quiet operation is expected, no room for a central plant. And the developer wants an electrification story under Local Law 97. You may have heard of Local Law 97. That's the local law in New York City that's getting rid of natural gas, which means we need electric heat. So if we're looking at our dominant constraints, footprint, right? We don't have a central plant. We need to have low noise, and we need to worry about our aesthetics. We have lots of zones, and we want to be electrification conscious, right? We need to have a sustainable, energy efficient solution. So if we're thinking back to our dominant constraints and our advantages and disadvantages, is this the right application for VRF, right? It seems like it might be. So it checks a lot of the boxes. We need to make sure the footprint is small, right? VRF has small indoor units, small outdoor units, and that's probably going to work out for us. The constraint here, right, is we need to have roof space, right? So our VRF system is very, very dependent on how much roof space we have, because every outdoor piece of equipment needs to be outside. In New York City, you don't have the luxury of hiding them in the bushes somewhere outside on grade. It's usually a very small roof footprint with many, many, many stories that you're going to have to cool. So you got to make sure that there's enough footprint on the roof for the amount of condensing units you need outside. Other than that, this seems like a great solution, right? So we're gonna check the box with the amount of zones. We're gonna be extremely energy efficient, and we're gonna hit our local law 97 target without using. We're gonna heat without using natural gas. So I think in this situation, we're gonna label this as a pro VRF situation, depending on if we have enough roof space. So on to the next example. Scenario B, right? So a historic renovation. This is a landmark building. We're gut renovating it. The new owner, landmarks in New York City and all over, you can't affect the facade of your building very much. So you kind of have to do with what you got. They're gutting the entire interior, which means we're not really changing the floor plate significantly. We're not really adding in huge mechanical plants. We're not adding in large duct shafts or chases. We have limited space for equipment. All these are the constraints for this project. And as you can imagine, we're going to have some mixed use zones for this type of building because it is a larger one, right? So our dominant constraints here are our footprint, right? We can't have shafts. We can't put in giant ductwork to lead down from the roof with our rooftop unit, right? So that maybe eliminates rooftop units. Aesthetics, we can't, we can't go through the walls. We can't put big units on the ground outside. So we got to confine everything to the roof. And the amount of zones that we have here is also going to lend towards VRF, right? So our major advantages are checked, right? Small footprint. We're going to have energy efficiency and zoning, right, with big diversity. And VRF seems like a pretty good application here. If we thought about rooftop units, maybe the ductwork is too big to go down the whole building. We can't do P-tax or V-tax because those will go through the windows. And as we know, landmarks, we can't affect the facade. We're narrowing down our field of equipment we can use out of our tool chest. And we're going to, say VRF is actually another good cause here. We can give it a go. So our next scenario is big box retail. We're a big, retail store in New Jersey, right? So we got a warehouse. Imagine your big Costco or Walmart or a huge clothing store. It's one large open zone with a single set point. The owner wants as low upfront cost as possible. We can imagine mom and pop shop, maybe not a Walmart. They have a lot of money, but we're going to think mom and pop shop here. They want a low first cost. They want it to be simple. They're not running huge facility staff who can maintain a system. And they want this to be simple, right? So maybe we look at a different system than VRF. So first cost is a constraint. We saw earlier that VRF has a larger upfront cost than package DX. One of the major pros and advantages is that it works really well with multiple zones with diversity. This situation, we only have one zone and it only has a single set point across the whole space. Maybe VRF's not great. And the owner doesn't want to think about it and then maintain it. They don't want a complicated system. They want it as simple as possible. So we don't really have any of the major advantages as a dominant constraint here. So I think that we want to look at a different solution for this project simply because we're not checking any of our major advantages. Let's go with a rooftop unit here, or maybe we'll look into another type of system than VRF. Scenario D, this is the same building as scenario A, right? We have our mid-rise hotel or multifamily hotel in the that was in New York City in scenario A, but now we're in upstate New York, right? We have the cold climate that we didn't have earlier. We have the owner in this situation is already committed to a central hydronic heating plant. They have a lot of space because they're not in New York City anymore. They're in a large, ground up building that's going to be built in upstate New York. And, they want a reliable code familiar backup heat because upstate has extreme cold temperatures that maybe are not going to be as perfect for our heat pump heating here. So in this situation, our dominant constraints are the cold climate, right? And the existing, maybe not existing central plant, but that the owner has already committed to it. They know that we maybe need a boiler because we can't get heat at low temperatures. We can't use our VRF system here because the owner wants to make sure in upstate New York on our negative 15-degree days, we're not going to lose heating. They want everyone to be nice and cozy and warm and have that full capacity of heating, even on our negative degree days that you could see quite often in upstate New York. That means they're going to use gas heating here or some sort of steam or some sort of major electrical boiler in order to get that heat at low temperatures. VRF in this situation is not going to be the right choice, even though it's the same footprint. That large building with multiple zones, we immediately can eliminate VRF because the owner wants to make sure that he has 100% heating on low ambient days. So while we check most of the boxes, we do have one constraint that immediately eliminates us from VRF. So, kind of looking high level, you can have many constraints pointing to one piece of equipment, and all of a sudden one constraint comes up. You can't use that piece of equipment anymore, and you got to pivot to something else. So this is a good example contrasted with scenario A, where it did work in scenario A, and now it doesn't work because of that one constraint. Scenario E, we have a mid-rise Class A office, right, in New Jersey, multiple zones. We're going to have a moderate floor plate. The developer already knows, they know a lot about different system types. They're comparing VRF versus a chilled water plant, right? We are tasked with choosing between these two. And the owner says first cost is a constraint, right? There's lots of zones. We have, lots of different offices, lots of different types of spaces, multiple facades, some of them heating, some of them cooling. And then they want it to be sustainable and energy efficient. So which type of system are we going to pick here, right? Right off the bat, it's not extremely obvious, right? You want to maybe say both could work, and you'd probably be right? Maybe we don't have enough information here to make the choice. Perhaps this office building, it's in New Jersey, right? We're not going to see those extreme temperatures of upstate New York. So maybe you're comfortable with having the heat pump heating as your only source of heat. You don't need a boiler. You don't need backup electric. The owner is basically choosing in this situation between having a central plant and running water throughout your building, or having rooftop equipment and having refrigerant run throughout your building. So those really come down to your 2 points. Let's say this owner all of a sudden thinks, I don't want to go with A2L anymore. That means you automatically have to go with your chilled water. But let's say the owner says, I don't want to give up any rentable floor space to a chiller plant, stick everything on the roof, then we have to go with VRF. So this is a situation where it could maybe sway either way, but it depends on the exact situation that you're dealing with. Maybe you need to ask some more questions after narrowing down your fields to these two pieces of equipment. And our last scenario here is a mid-size office, right? Many projects that we do here in Manhattan are, office type buildings. We're in New York State climate, New York City zone 4A. There's many zones. And it makes sense for a VRF fitting, right? We don't have any central equipment rooms, but we do have heavy outdoor air loads and a ventilation requirement. There's maybe a swimming pool that has a high humidity. Maybe there's a space with lots of people in it, which drives our outside air ventilation rates up. And our VRF system alone cannot handle the system. So we're going to have to pair this with a VRF, or we're going to have to pair our VRF with a DOAS solution in order to get rid of that humidity before it reaches a VRF. So we're actually in this situation, which is one of our most common situations with VRF, is to pair this with a DOAS system to handle latent loads, and our VRF system is going to handle our sensible loads at each zone. Together, these two systems will be extremely energy efficient. That way, your VRF focuses what it's good at, and your DOAS focuses on what it's good at. You don't have one system that's trying to do both, and it maybe is not as efficient at it. So in summary, we only have a couple minutes left, but as I said, I made a promise, and I got to follow through on our promise. We want to be able to recognize what VRF systems look like, right? We have outdoor units, indoor units, branch selector boxes, and our controls. Each piece of this system makes up our VRF, right? Next, we learned about how we actually transfer the heat with this VRF system, right? We're still moving our heat from the indoor space to our ambient air. And how do we do that? That's with the refrigeration cycle. VRF spreads that refrigeration cycle throughout the building, running refrigerant between an outdoor unit and an indoor unit. And as you can remember, we are manipulating pressure, right? Our pressure dictates our temperature. And by varying our compressor speeds and our expansion valve, we are changing our pressure and getting different capacities at our zones. So our controls loop, our VRF and refrigerant loop, and our air side loops are all working together in order to get a very energy efficient solution here. My next promise was, let's look at the constraints. What are the major pros? What are the major cons? Footprint, zoning and diversity, and sustainability and energy efficiency are going to be the major pros that you look for. And that would mean you are going to use a VRF. But the major downsides are, if you have one zone, if it's extremely cold climates, or if there's a large latent load, maybe you want to look at a different system, or complement this with a DOAS in order to make that system work properly. And lastly, we went through all those examples. As I said, in the examples, every project's going to have a different list of constraints. It's your job to figure out the dominant constraints. And once you figure out which ones are the dominant ones, you can decide, is VRF the right solution or not? And because this is PDH, we got a couple credits here at the end. So first question is, in a VRF indoor unit, how does the coil absorb heat from the room? A, compressing the circulating room air. B, boiling refrigerant through phase change. C, storing heat inside chilled water. Or D, radiating warmth towards cold surfaces. So I'll give you guys a second. And the answer is B, boiling refrigerant through phase change, right? We learned in our refrigeration cycle that we are actually moving heat by boiling or condensing our refrigerant. So that answer is B. Question 2, which loop does VRF eliminate compared to a chilled water plant? We think back to our 5 loops, they're on the bottom of the screen. Maybe that's a hint, but A, air side loop, B, refrigeration loop, C, chilled water loop, D, controls loop. I'll give you a second to figure out the answer. And if the bottom didn't give it away, it's C, chilled water loop, right? We only use our air side refrigeration and controls loop in a VRF system. And last question, a VRF system almost always needs which partner system for ventilation and humidity? A dedicated outdoor air system, B, central cooling tower bank, C, a backup electric resistance coil, or D, a standby diesel generator set? I'll give you guys a second here to think through this one. All right, so this one's a little trickier maybe. We can immediately eliminate B and D, right? We don't have a cooling tower here. We know we're not using the heat rejection loop. It's not highlighted at the bottom of the screen. And D, we don't really need a generator set. That's not really, that doesn't have anything to do with our ventilation and humidity. So we're down to A and C, right? A dedicated outdoor air system or a backup electric resistance coil. While we might need electric resistance coils for low ambient temperatures, that doesn't have anything to do with our ventilation and humidity. So we narrowed it down. The answer is A, a dedicated outdoor air system. And so that's it. Thank you everyone for joining. We just finished our VRF systems. Next week, we're talking about rooftop unit fundamentals, and we'll have the recordings from last week and this week posted by the end of the day today. So you can access these. Reminder, next Thursday at noon, same time as VRF, our rooftop unit fundamentals.
Jack, absolutely awesome job here. I never thought I'd learn so much sitting on the beach. So thank you very much. Thank you everyone for tuning in, and we're excited to see you next week. So have a good rest of your day and go Knicks. Thank you very much.